So just to proceed with the previous calculation, if this is how the amplitude will fall, then let me try to explain what will be the corresponding time period. Then you'll have a comparative understanding. Okay. Now you see the graph which shows you the displacement over here. Well, if you just look into the time period of oscillation, which is, if you call this as t prime. Okay, so what is your t prime? T prime will be equal to 2 pi by omega prime, isn't it? So that is your t prime, 2 pi by omega prime. So 2 pi by omega prime is equal to 2 pi by square root of omega 0 square minus k square. It is equal to omega 0 square minus k square. Okay, alright. So if you really substitute the value for omega 0 and k, well, you can show that, well, this is actually equal to, let me write it here itself. This will be actually equal to 2 pi by square root of S by M minus R square by 4M square. Just by putting the value for omega 0 and k. Okay. Okay. Alright, if you just put the values, this is what you will be getting. What will be the frequency? Because these things you'll need for your problems. What will be the frequency? F prime. F prime will be equal to omega prime by 2 pi. Okay, so this is equal to 1 by 2 pi square root of S by M minus R square by 4M square. Okay, and what is your natural frequency? F0, if you remember, for an undamped motion, it is 1 by 2 pi just square root of S by M. So what is your observation? That the frequency of damped oscillation is less than the natural frequency of vibration, isn't it? So that is what we observe over here. Now suppose, say, in damped oscillation, we take an electrical circuit. Alright, consider an electrical circuit in damped oscillator. Okay, so if you do it, you see here. So in an electrical circuit, what do we observe here? Well, we will be having a resistance. Okay, now, okay, an inductance. All right, and then, well, you will be having now a capacitance. Why a resistance? Because now the damping will be provided by the resistance, a capacitance. Okay, I'm just considering the electrical analogy. All right, so, well, here you have your switch K. All right, and here is your battery. All right, so you see, how do you generate the equation over here? Okay, what is the mode of generating the equation over here for damped oscillation? So for whatever voltage you are generating, okay, you see V is equal to, here V, C, the voltage is equal to Q by C. Okay, here the voltage, the back EMF across the inductor here. Okay, so VL, if I call it minus L d I dt. Okay, and then, well, what about the voltage across the resistance? VR, it is equal to IR, isn't it? So, well, therefore, how will you write down your equation over here? The sum of all the voltages, if you just consider, okay, what will you get over here? What will happen if you consider an electrical circuit like this containing a resistance R, inductance L, capacitance C, okay, and they are connected to a battery and a key. This is a key, this is your battery. Now when the key is pressed downward, if you just press the key, the capacitor is charged. You charge your capacitor. Alright, so let Q0 be the charge on the capacitor. Alright, now when the key is released, when you release the key, what will happen? The capacitor circuit is completed through the inductance cell, alright, and the resistance R. The capacitor slowly loses its charge, due to which there is current I at any instant. This current will vary at the rate di dt. Okay, now if Q is the charge on the capacitor at any instant of time t, then these are the potential differences that will be operational in various portions of the circuit. Okay, so we can say over here that Q by C plus Ri is equal to minus L di dt. Okay, all right. So what can we say over here? Ultimately, therefore, we can say that L di dt plus Ri plus Q by C equal to 0, isn't it? Now I is equal to dq dt and di dt is equal to d2q dt square. Okay, so you see, therefore, well, L d2q dt square plus R dq dt plus q by c is equal to 0. Okay, so what do you get over here? Or d2q dt square plus R by L dq dt plus 1 by LC q equal to 0, isn't it? So this is how the differential equation for an oscillator, for a damped oscillatory circuit will evolve, where you now get it similar to your equation. Let R by L be equal to 2K and 1 by LC is equal to omega 0 square. So that finally you write your equation as d2q dt square plus 2k dq dt plus omega 0 square q equal to 0. Okay, so from here now you can write the solution for q. For an oscillatory circuit, see, the oscillator will die out. E to the power minus kt, okay, into, what do you get? A1 e to the power square root of k square minus omega 0 square t plus A2, isn't it? Let me write here, A2 e to the power minus square root of k square minus omega 0 square t. Okay, all right. So this is what you get as your solution to your oscillatory motion. Now let us consider, here also you will get the conditions of heavy damping, critical damping. For light damping, if you go for light damping, okay, for light damping, what is the meaning of light damping? Well, k square less than omega 0 square, isn't it? What do we see? You will see r square by 4l square is less than 1 by lc. Okay, you will observe that. Okay, and well, the condition for the discharge to be oscillatory, therefore this is your condition for the discharge to be oscillatory. Discharge to be oscillatory. So these you will know require in your problems. Under what condition will it be oscillatory, or will it be oscillatory or not, if you're asked to check in a circuit. And you can show over here as the well-known expression for the time period t. T will be equal to 2 pi, okay, square root of 1 by LC minus r square by 4l square. Now obtain frequency from here. Obtain the frequency. Okay. Let me get the expression for frequency. Get it ready for me. Alright. Let's stop over here and let's go to the next slide.